We are very happy to have Stefan Waldmann, and he's going to talk about convergence of star products. Please.
Yeah, thank you very much. And thank you very much for the invitation. And in particular, since this is a long-standing invitation and only now I made it, it was possible for me to come. So apologies for not showing up before. So anyway, it's a great pleasure to be here and to see so many familiar faces here again. So the topic of the talk is an ongoing project for many years now for me. So it's about convergence of star products, and I mainly will talk about one example, and do a couple of general things before, but mainly we'll talk about an example. So this is, of course, I guess for most of you, well, I will offend the C-star algebraic people doing differential geometry and algebra. I will offend the algebra people because I'm talking about semi-norms. And so I essentially will offend everybody here, I guess. Yeah? And so we are on equal terms in the end. Yeah. So there's no preference. Yeah. So the problem arises, well, I have to give a bit of motivation. And that will be for me formal deformation quantization. And so let me just recall a bit the basic notions here. And there is, of course, a huge story behind formal deformation quantization. Way too much to be recalled in just one talk. But the setup is the following. We start with a Poisson manifold. And thinking of this Poisson manifold as a phase space of some classical mechanical system. Yeah? So that's the motivation. So our starting point is doing some Hamiltonian mechanics. And then we want to construct the corresponding quantum theory for that classical system. And construct this way, that's pretty optimistic. Yeah? I would say guess is the better word here. Yeah? We want to have some heuristically motivated list of axioms or requirements. Once we fulfill them, we might end up with something like the quantization of this classical system. And so the first idea is, well, we have to focus on algebraic features, yeah? Because quantum theory is not a geometric theory. It is about operators on Hilbert spaces. So we should talk about algebras of observables first. And we can formulate Hamiltonian mechanics in a algebraic way. So we pass to the function algebra, and we get a Poisson bracket from this Poisson tensor. So this is a Poisson algebra. And this is sort of the classical observable algebra. And now we would like to cook up some corresponding quantum observable algebra. And what is the idea? Well, for every classical observable, there should be, in some sense, a unique quantum observable. Yeah? So for energy, there should be also an energy operator. For classical momentum, there should be a momentum operator. For angular momentum, there should be an angular momentum operator. And so that would, first of all, suggest, well, we are talking here about a bijection. We want to find a bijection between classical observables and quantum observables. The problem is that already here, we've made some quite drastic idealization from a physical point of view. Yeah? I mean, all smooth functions, I mean, from the point of view that observables should be in principle measurable quantities in the lab from your colleagues, yeah, you have to argue how to measure such a function, right, of the position. He will tell you, no, I don't measure that one, I can measure position, and then I can compute this function. But that's not what quantum mechanics will then tell you. So all smooth functions are classically an idealization, and you can view it mathematically as a certain completion of some true observables which you figure out in the lab, yeah, by some suitable topology. Yeah? And it's for convenience, it's easier to work with smooth functions on a manifold rather than some obscure subalgebra of it. You know? Even though this subalgebra might be dense, yeah, in the usual Frechet topology or whatnot. Yeah? But you see, this is a kind of idealization. And quantization, that would mean, well, you have to figure out the true observables, and then you might have to expect a bijection to the quantum observables. And then again, on the quantum side, we know that, well, people love to use C-star algebras because they have a good spectral calculus. Yeah, that's where C-star algebra came from, actually, that we have a good notion of spectrum, that spectra behave of Hermitian elements behave in the way we want. But they also involve completions, right? That's again a physical idealization. Not to every operator on Hilbert space you can really build up an experiment in the lab. Yeah? This is a way too drastic idealization. It's just made for convenience to maneuver you into a situation where quantization, where spectral theory and mathematics becomes feasible. Yeah? So, nevertheless, the idea is that as a first step to cooking up a good observable algebra on the quantum side, we just keep the vector space we have. Yeah? We know this is an idealization, and there might be functions which we have to kick out in the end again. Yeah? But we keep the vector space, and the only thing which we want to change when passing from classical mechanical systems to quantum mechanical systems is the passage from commutativity to non-commutativity. So we just cook up a new product which is modeling the operator composition. So you can think of that also as an abstract version of a symbol calculus, if you want. Yeah? So these are playing the symbols, and you have a composition of operators, and you transport it back to a composition of symbols. Yeah? So keep this as vector space and change the product, the usual product of pointwise product of functions, to a non-commutative product. Can you see that like that? Product. Let's call this star, corresponding to quantum theory. Yeah? Yeah? So the advantage is that then we have no longer this problem of idealization. We just have the same interpretation of the elements here. We know exactly what is energy. We know what is angular momentum because it's simply the same function as before. That's the advantage of this point of view. Yeah. So the meaning, the physical meaning of the observable stays the same. It's only the product rule which changes. Yeah. And so the axioms of a star product. Yeah. What do we want? Well, we want that the product is, of course, associative. Yeah, because composition of operators on a Hilbert space is associative. Yeah. Then we want that we have a classical limit, and that is where now the additional ingredient comes in. That's the Planck's constant. We want this product sort of depending, I should put this here, on a parameter, which is Planck's constant, which is h bar. And so we want this to be the classical multiplication if h bar is negligible. Yeah? So as physicists do, we make power series expansion as a kind of perturbation around the classical situation. Quantum effects are small in most cases, right? I mean, classical mechanics is not entirely bad. In fact, it's a super good approximation for many purposes. Yeah? So we want something like that, and then we need higher orders in h bar. And to incorporate the non-commutativity, well, we look for the commutator of this new product, and then, of course, the lowest order drops out. Yeah? And then we have to pose a condition in the next order. And commutators of an associative product are a Lie bracket. So it's very reasonable to put a Lie bracket here as first order. Yeah? And so the Lie bracket we put is the Poisson bracket we start with. That's the correspondence principle, what survives from this original Dirac ideas. Yeah? So this is essentially the definition of a star product. Yeah? And then you might add some more technical conditions about how the higher orders look like. And now the difficulty, is the following. We need higher orders to get associativity. So if you say, well, let's start with as the first try for the star product with pointwise product plus half of the Poisson bracket and stop there, then these two requirements would be fulfilled. Yeah? But this one would fail in order h bar square. So we need another term in order h bar square to compensate for that failure. Suppose we can fix that, then we look at the new product and the associativity in order h bar cube. And then we will see, well, that fails. Yeah? We need another correction term, and this will never stop. Yeah? This one can show more or less easily. Yeah? So for a generic enough Poisson bracket, you need all higher orders. Yeah? So that means what we need is something like that. So we expand our new product in powers of h bar, and then we have some coefficients which we have to choose in a clever way so that the overall product is associative. And now you see, well, now I should better explain to you what this really means. Yeah? Here's an infinite sum now appearing. Yeah? And so either I tell you under which conditions this summation converges, what is that this is really a convergent series, yeah? Or the cheap way out is to say, well, actually I don't care. Yeah? Now I'm switching my role from physicist to mathematician and say, well, perfectly fine, formal power series. That's all I care. So the first step is, and that is what is formal star products. Yeah. We work over functions on the manifold, but with formal power series with coefficients in the functions. And then this is a nice definition. Yeah. This is a nice thing to look at. Yeah. And you see that if you look at examples, I have not given you yet an example, but if you look at examples, what you see is that in examples, that these CRs are bidifferential operators acting on smooth functions of order, well, something like RR. So in each argument, we have R derivatives. And that's very bad, yeah? Because then that means that here we're collecting, at a given point, we're collecting the infinite Taylor information of f and g. And as long as we work with smooth functions, you know, by this classical lemma of Borel, you can adjust the Taylor expansion of a smooth function in an arbitrarily nasty way at zero. Yeah? You can mess up convergence always. Yeah? So there's no hope, yeah, that such a series can possibly converge for all smooth functions for h bar non-zero. Yeah? So this is this gives a big problem. And that's the Borel lemma. So if you believe me that, yeah, that all examples we know are of that type. Yeah, I mean the Borel lemma, so there's no convergence. Yeah, so this we can forget about. Yeah, no convergence for f and g being generic smooth functions. Yeah, this is simply not feasible. So that's bad because we wanted to do physics in the end, and h bar is not a formal parameter, but it's one in natural units. Yeah, so this is not this is a constant of nature, which is not at our disposal. Yeah, there's no little wheel where we can adjust the value of h bar. Yeah, this is h bar is fixed by nature. Yeah, so that brings me now to the second step, the general strategy, or if you want, the wish list. What we want, we want to solve this problem. We want to cook up an honest algebra over the complex numbers, not involving formal power series. And in the end, we want even maybe a C-star algebra. Yeah, you'll see it's a long way to get C-star algebras. Yeah, this is not at all a C-star algebra here. Yeah, so the ultimate goal would be maybe some nice C-star algebraic completion of some convergent star. We'll make this a bit more precise in a second. Yeah? So we need to talk about convergence, yeah, for physical reasons. And as we have seen here, it will be definitely necessary to restrict the class of functions. Yeah? So we will have to specify better functions than just any smooth function. Yeah? So need nicer, whatever that means, subclass of functions inside the smooth functions, but certainly not all of them. Yeah? And then, of course, you see this will become, of course, complicated, yeah? Because on a generic manifold, you have smooth functions. You have maybe smooth functions with compact support, but without any further structure, there's nothing in between. Yeah, I mean there is no good choice. Yeah, so you need extra structure to specify such a subclass of functions. Yeah? And so that ultimately already indicates that, well, we will have to talk about examples first. Yeah, this is we can make a wish list. Yeah, and I will do that. But ultimately we have to look at examples. Yeah, it's very hard to imagine that there is a general theorem about this. Yeah, this would mean that for given a Poisson structure already on a manifold, on a generic manifold, there is a subclass of nice functions on it. This is hard to imagine. Yeah, I mean, in this full generality, this is hard to imagine. Yeah? And since we know, I mean, I should have said that, yeah, these star products, they always exist. Yeah, I mean, for any Poisson structure, we get such star products. Yeah, the formal star products. That's the big theory of formal star products. I mean, there are many names involved, like Convergence and many others. Prove this, that we always have that. There's a classification available and all these kind of things. But this will bring us back to examples here. Here we cannot expect something general, I think. Yeah. So nevertheless, the strategy will be the following. So let's first look at an example that you believe me that these kind of things exist at all, right? So let's take as manifold Rn, let's take as Poisson bracket of F and G the usual canonical Poisson bracket. You can do that also in higher dimensions. Let me just do it in 2 dimensions to get less indices. Yeah? So that's the usual Poisson bracket of classical mechanics. The 2 coordinates are P and Q. Yeah? And now we can write down a star product, which I will call the standard ordered star product. And so how is that done? Well, I will write down the formula and explain it in a second. So this will be an exponential type star product So we take f and g, the two functions, take their algebraic tensor product, act on this algebraic tensor product in the sense of formal power series in h bar with this exponential of, if you see, half of the Poisson bracket. And I think I should do it the other way around, actually. This way I should do it. With a half of the Poisson bracket and exponentiate that. And then this mu, that is just the usual product, the pointwise product of functions. Yeah, that's just an abbreviation of collecting funny derivatives ordered by powers of h bar, and that can also be written, if you want to write it in that way. So this is 1 over r factorial h bar over I to the r, and then the f will be only differentiated in p direction, and the g will be only differentiated in q direction. Okay? Yeah.
Maybe just back up a little bit to this issue of special subclass of functions.
Yeah.
If you were in a more special case of cotangent bundle,
for example,
manifold, then
we will actually do that. Yes.
Okay.
Yeah. No. I mean, the moment you know more about your manifold,
yeah.
you have maybe candidates.
Right.
That's exactly what I say. Yeah. You have to invest more. Yeah. You have to invest some more knowledge about the geometry of M.
Okay.
Yeah. For example, being a cotangent bundle. For example, carrying an interesting enough Lie group action so that you have representative functions or whatnot. Yeah. So I mean, there will be situations where you have good candidates. Yeah. And this will be exactly the ones I'm talking about.
So in the cotangent bundle case, something like symbol calculus would make an appearance. Is that
it will not work in general, yes, because simple calculus is an asymptotic formula which is not convergent in the topology of. I mean,
okay,
this is only
something more special.
You need a bit more than that. Yeah, well, simple calculus is the motivation for most of the things I will do, but I really want to sort of have convergence and not convergence modulo smoothing.
Mm-hmm.
That will be the point. I mean, that's okay. You may argue why this is interesting, yeah, but I think it is interesting. Yeah?
Okay, thanks.
Okay, but if you have questions, please interrupt me anytime. Yeah, I should have said that in the beginning. Yeah, so don't be shy. Yeah. Okay, so that's why you asked this question, right? I mean, this is exactly the simple product, yeah, of the standard ordered simple calculus. That's why it's called the standard ordered star product. Yeah? So little exercise for the students, prove that this thing is associative. Yeah? This is not too bad, but requires some tricks. You can do it in a brutal, direct, rough way. Yeah, that's really the first attempt, or you can kind of do it in a bit more clever way, making use of this structure here, and that these kind of guys up here are derivations which commute. Yeah, and whenever you have a exponential of something, some commuting derivations, that's an old trick of Gerstenhaber from the 60s, and this gives something associative. That can be applied, but you can do it really on the nose. It's not. There's no secret. Yeah, it's just a matter of writing things down. So this is a star product, and in fact, now we are using the following observation. Our R2, and that's exactly what I was telling, is the. I interpret that now as a cotangent bundle of the real line. Yeah? So P is really the fiber direction, and Q is the spatial direction of the configuration space. Yeah? So, and then what I observe here for this product is that it's interesting to look at polynomial functions on the cotangent bundle that you can do for any cotangent bundle. So what does that mean? This is a function which is smooth on the cotangent bundle, on the total space, such that if I restrict it to a cotangent space, yeah, this is polynomial. Yeah, for all points in the base. And this definition makes sense also for I can replace here this R by any Q. Yeah, this makes sense for any configuration space. Yeah, polynomial functions on a total space of a vector bundle. That's an intrinsic notion, but it makes use of the vector bundle structure you have. Yeah, so that's the additional information which we invest now. Yeah? You can forget about that this guy is a vector bundle, then it's just R2. Yeah, or you can keep that information. You could also, of course, say, well, this is even a vector space. We can also talk about linear functions in Q, but then it's very special. Yeah? This is very general still. Yeah? I mean, any manifold can be used here. Yeah? And now you see that if f and g are polynomials, then you see that these derivatives stop at some point. Yeah? This will only be a finite summation. And the result will be again a polynomial in P, no matter what the dependence on Q was. Yeah? So here we see that this thing here is again a polynomial, and in fact a finite sum. So we have convergence. Well, for trivial reasons, yeah. I mean, it is a finite sum in the end. Yeah? And we have found a subalgebra, very small one maybe, where this thing converges. So let's take this as an example and try to extract some, yeah.
Star products. So is there a categorical counterpart of this notion? Like some structure of monoidal categories?
Well, I mean, there's of course a way more abstract notion of deforming associative algebras by Gerstenhaber. That's an example of an associative deformation, a formal associative deformation in the Gerstenhaber algebra sense. So that's maybe the framework which you're looking at. Yeah?
But I mean, so if you think just about algebras, you get monoidal categories. So yeah, with the extra structures, of course. But I was wondering if you add this Poisson structure, what do you get on the category theory?
I mean, this Poisson algebras, they also form a category, if you want. Yeah. So this is a program which sort of makes sense for any Poisson algebra. You could, in principle, ask for whether there is a formal deformation of it or not, and classify them and so on. Yeah. This you can always do. Yeah. And in fact, you can also say, well, if I have an associative commutative algebra, yeah, and if I find such an associative deformation, you can reverse it. You can prove that the first order term, the antisymmetric part of the first order term, is necessarily a Poisson structure. Yeah? So the question is only which Poisson structures can be deformed. Yeah? I mean, you always have a Poisson structure in the game, whether you want it or not, at least if you start with something which is commutative. Yeah, I mean, this is commutative. These are functions. Yeah? Of course, you can also, and Gerstenhaber did that, deform non-commutative associative algebras in an associative way. Yeah? This is also interesting. Why not? Yeah? But then you don't have a Poisson structure to as a kind of infinitesimal first-order deformation. Okay? Good. Thank you. So let's raise that here a bit. So what did we see now? Well, we saw that there are apparently examples, at least I gave you one, where this kind of convergence issue looks pretty harmless. Yeah? I mean, this is a finite sum, so what could possibly go wrong? And in fact, there are many more examples of that type. Yeah? The only drawback, if you want, is the following. Polynomial functions on the cotangent bundle, they might be not super interesting per se. Yeah? Many physical observables will be in there. Yeah? The angular momentum, all the momentum functions, your typical Hamiltonian, which is kind of a quadratic polynomial plus some constant term for the potential. So many of your observables are in there. So if we can do something for them, well, that's fine, perfect. But there will be others which we need for quantum mechanics, which are not in there. Yeah? And that will be more transcendental functions. And now you can think of, well, we need something more transcendental in the momentum direction. Yeah? So is there a quantum observable, an object in quantum mechanics, which is not a polynomial in the momentum direction, which you would like to talk about? Well, I guess so, in the moment you want to have the unitaries, yeah? the time evolution. Yeah? They will be exponentials of these guys. Yeah? So for that kind of reason, it would be nice, yeah, to have a bit more than that. Yeah? To have a kind of a bigger space of functions where we still have the nice, funny multiplication, but with more general dependence on the momenta than just polynomial ones. But then you see, you run immediately again in this problem. Then we have infinitely many derivatives here, and then convergence becomes an issue. Then we have to worry about convergence. Yeah? So the strategy is now the following. Well, strategies, it's more a wish list for Santa Claus. Yeah? It's not really a strategy. Yeah? So we start with a subalgebra A in the smooth functions on our manifolds with formal power series for the star product with kind of trivial convergence. Yeah? Like something there, polynomial functions on a cotangent bundle. I should say that you can do the same kind of, I mean, the formula becomes way more complicated on a generic cotangent bundle. It's not that easy to write down a formula anymore, but there are star products having the same feature that the polynomial functions are a subalgebra and all the summations are finite. Yeah? These kind of things exist on any cotangent bundle coming from a simple calculus, but from a global simple calculus using connections and not just from this local simple calculus glued together by partitions of unity. Yeah? So you have to work a little bit. So a sheaf theoretic approach is in some sense not enough. You need really a global simple calculus. In any case, we're doing smooth differential geometry. We have connections. There's no problem from that side. Anyway, suppose you have that. Yeah. Then second, what do you want to do? Yeah. You want to find, let's say, locally convex topology on A such that star is continuous. Yeah? So if we succeed in doing that, and we have a locally convex topology, so built by a bunch of semi-norms, such that the product is continuous, then we know by abstract nonsense the product extends to the completion in a continuous way, uniquely. So that's then cheap. So extend star by continuity to the completion. Let's call this A hat. Yeah? So of A. Yeah? So, and then we hope that this algebra is now bigger, contains more interesting functions, and it has a nice product which is even continuous for a nice topology. And then we can hope for, well, implementing these guys as maybe operators on Hilbert spaces or things like that. And we can start to continue working with a nice topological algebra. Yeah? So the difficulties, this is definitely plural. Yeah. So what can go wrong? Yeah. What? I mean, it's a wish list. Yeah. Start with can go wrong. Yeah. I mean, I have no idea how to find that. Yeah? This is by no means an easy feat. Yeah. This is, you get one only by luck. There's no, up to now, I have no mathematical statement guaranteeing the existence of a interesting enough subalgebra where you have trivial convergence, yeah? like in this example there. Yeah? So in general, no way. So we need examples. In examples, we might be able to do that, yeah, by staring at the example and using very specific features of the examples. In general, I have no idea. First step fails, which is in some sense good news, so we don't have to worry about the second step, yeah? Because this is also completely unclear whether this exists. Yeah? So even if we succeed with finding this subalgebra, it's not clear how to find this topology. And if I mean not clear, then this means that there is no universal mechanism responsible for that. You could say, well, finding locally convex topologies for a given problem, you usually say, well, I take the coarsest or the finest locally convex topology such that blah, 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 blah holds. But the problem here is that for the continuity of a product, that's a bilinear map. Yeah? So if we want to find a mu which is continuous on A, we could say, well, let's take the coarsest topology on A such that this map is continuous. But, wait, we also have to find the topology here. It's not given here yet. Yeah? So if it would be given here, we could take the coarsest one there. Doing it the other way around, say, well, we look for a topology here. Let's take the finest topology here such that this map is continuous. Bad idea, because we don't have the topology here yet. Yeah? So this is the problem where you have no universal property giving you a good candidate. Yeah? So this is obscure. Yeah? How to get that. Yeah? And again, in examples, by magic and whatever tools you like, by some way more arcane techniques, you might be able to succeed. But this is there's no general construction, no general feature here, yeah, to guaranteeing continuity of a given bilinear map. Yeah, if you want to find the topology on the target and on the domain at the same time. Yeah. So third part, that's good news, is, well, once we are here, then this works. that's by general nonsense. Yeah. So this is kind of the strategy, and what I want to show you now is that, well, we do have a couple of examples where this strategy really can be carried through to the end. Yeah. And this is. And at the moment, we are still in the situation where we are collecting examples. There are some patterns which show up by now, and one gets some, I would say, experience or instincts how to handle these kind of two steps, 1 and 2 there. But it's at the moment, well, we are more modest and just looking for examples. Maybe just to give you a little idea what the level of the problem is. Yeah? For this star product, the commutator of Q and P is 1, yeah, IH bar 1. Yeah? So you have canonical commutation relations inside that algebra. And the moment you have canonical commutation relations in an algebra, you can show that there is no submultiplicative seminorm, let alone a norm on this algebra, beside 0. Yeah? 0 is a submultiplicative seminorm, but that's the only one. Yeah? So I don't even dare to speak about Banach algebras here. Yeah? I know this is doomed. Yeah? This we can forget. We need at least a Frechet setting. Yeah? We need at least countably many seminorms. With one seminorm, continuity is not achievable, full stop. And we can also forget having submultiplicative seminorms. Yeah? There's a lot of literature on projective limits of Banach algebras, yeah? on Frechet algebras or locally convex algebras with submultiplicative seminorms. They're also called the locally multiplicatively convex algebras. Sorry, this is not our domain. Yeah? This technology doesn't apply. Yeah? This is unfortunate, but that's the nature of the problem, the very nature of the problem. We are dealing with canonical commutation relations, so all this technology is not available. Yeah? Just to gauge a little bit the level of complications which we have to expect. Yeah? Okay, so now let's look for an example. And the example will be the cotangent bundle and the cotangent bundle of a Lie group. Yeah? And so this one will fit in there. Yeah, I mean, this is the cotangent bundle of the Lie group R with plus. Yeah, so this will be a part of it, but let's try to do it a little bit more general. Yeah? So how do we approach this? Well, first of all, cotangent bundle for Lie group by left trivialization becomes a Cartesian product of the Lie group and the dual of its Lie algebra. So that means that the functions on the Lie group, they, well, are kind of functions on this, well, isomorphic too. Yeah? And then I will always make use of these isomorphisms here. Yeah? Will be functions of two variables, group variables and Lie algebra, dual of Lie algebra variables. And one can now say, well, what are the polynomial functions in this sense? Yeah? That restricting them to a fiber, they are polynomials. Yeah? So these are just the fibers. Yeah? This is a trivialization of this guy as a vector bundle, not just as a manifold. Yeah? This is really the global trivialization. So what we get is coefficient functions times polynomial functions on G star. Yeah? And this is not, there's no need to complete here. This is a direct sum. Yeah? This is really all what the polynomials really are. Yeah? So this is an algebraic tensor product, and because we have here a trivial vector bundle, yeah? We have global frame. Now again, we can rewrite this as coefficient functions, and that's the symmetric algebra over G. Yeah? We are finite dimensional, so the polynomials on the vector space are the symmetric algebra over its dual and vice versa. So we can view these guys as symmetric tensor powers of G. And the degree here is really the polynomial degree. So that means if we want to specify a star product, we have to specify it on these two tensor factors. Yeah? Then it would be okay. Let me just see if I get here back my formulas. Yeah, and so we want to specify a star product on the cotangent bundle of our Lie group. And well, there's a long story behind, and this was originally constructed, well, not precisely this one, but kind of a more Weil-ordered star product by Simon Güth, 83, yeah, and was then reconstructed by very different means by our former Freiburg group of Martin Bordemann, Nikolai Neumann, and myself in the 90s, later 90s. That's the construction I'm using. That was a construction for star products on any cotangent bundle, coming from this simple calculus idea. And so I'm using now this formulas from there. Yeah? So the ingredient, what you need to cook up this star products on cotangent bundle is a covariant derivative on the configuration space. And the nice thing about the Lie group is that it has a canonical covariant derivative. That's the half commutator connection. Yeah? There's a super nice, maximally invariant under all ways the Lie group can act on itself covariant derivative. That's this half commutator connection. Yeah? And this we use for building the simple calculus, and then we get a star product. Long story short, I give you a formula for it. Yeah? And it's not easy to check that this is associative. So we have to specify it on here and on here. Yeah? So and the first thing is what we do is we have the symmetric algebra, and you know that as a vector space by the Poincaré-Birkhoff-Witt theorem, this is the same thing as the universal enveloping algebra. Actually, as a co-algebra, it's the same. And what you can do is you can, well, plug in a little h bar at the correct position, compatible with the filtration of the universal enveloping algebra, so that you get a star product here. This gives what is called the good star product. I should write it like that. Yeah? This is the good star product on the symmetric algebra. And I should put a complexification here because we want, I forgot to, it's already erased. I mean, we are physicists by heart, right? So there should be an I in the star product here at this point. Yeah. So that's why we need complexifications. Yeah. So that's the star product of Simon Good from 83. And in fact, by coincidence, also in the famous Drinfeld paper on quantum groups on 83, this star product has an appearance, I think, in a footnote. Yeah. So for him, this was obvious, yeah, that this is a star product, and Simon Good used that star product with a different argument, but not only for here, but then she extended this thing really to the cotangent bundle. Yeah. So that's what the, if you want, the big good star product is, and that's the little good star product here. Yeah. So this one. So this is, you see, you have a explicit formula for this thing up to Baker-Campbell-Hausdorff. Yeah, so whatever you consider to be explicit. Yeah. Suppose you have good knowledge about your Baker-Campbell-Hausdorff series for this specific Lie algebra, you can write down a formula for that thing. Yeah? I can write down the formula for this star product in terms of the Baker-Campbell-Hausdorff composition law. Differentiated many times, and Taylor expanding the BCH term up to blah, 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 many brackets. And so you see, in general, it's very messy to get really explicit ones, but you get kind of good enough formulas to do estimates. Yeah, that's the kind of the privilege of doing analysis. Yeah, nobody cares about explicit formulas. You can be rough. Yeah, this is the good news. Yeah, you can just estimate things, and that's all what we want. Yeah, I mean there is of course an explicit, precise formula, but you never have to look into the very details of that formula. Yeah? So the idea is, since we have here a tensor algebra. So this is the big direct sum of symmetric powers of G. So we need to cook up first a topology on this guy. Yeah? And then we have to do something about that tensor factor, and then we have to combine things. So we first look at this one. This will be the invariant polynomials, if you want, on the Lie, the cotangent bundle of the Lie group. So they should also carry a topology already. And let's try to find that. So, and that's kind of the trick we have been successfully using now for many years and in many situations. This is the following topology. So, given any semi-norm here on G, so given semi-norm P on G, consider the following, which I call PR, a semi-norm on the symmetric algebra. I will build a new semi-norm to do estimates on the symmetric algebra. So this will be then some psi R going from 0 to up to some, I mean, this is a finite sum. Yeah. So this is by degrees of homogeneity here. Yeah. So what do I do? Well, I take the rth tensor power of this seminorm. There's a canonical way to extend the seminorm to tensor products, tensor powers. That's the projective topology, which you do put on the tensor power. So I can put this on here. Yeah? the point is I have one reference here, and then I know already all its tensor powers. And then I sum them. And I sum them with weights. And let's sum them with weights like that. So fix R bigger than 0, then I can construct out of any given seminorm on the vector space a new seminorm on its symmetric algebra by doing that. And now you ask, okay, why should I put here n factorial to the power R? And the answer is very easy, because it works. Yeah, but that's the magic. Yeah, I mean, this is by looking at things long enough, and I think there's no deeper explanation of that beside that it works. So there's a.
Just to clarify, you're not trying to come up with seminorms that would make this symmetric algebra space complete already.
No, they are not yet complete. That's the whole point. I want the completion to be as large as possible. Right. Yeah, I want to have I mean, otherwise, if I want this to be complete, I would take the finest locally convex topology. Yeah. That would be it. Yeah? And then, in fact, this thing is also continuous, I think, for the finest locally convex topology. But then I don't gain anything. Yeah. Then this is just all I have. Yeah. And I want to have a hopefully very large completion, so that I have interesting elements in the completion, some transcendental functions. They are not just polynomials.
Okay.
Yeah. Okay. So then the theorem, first theorem is, and that is by Esposito, Dapor, and myself, is that this star G is continuous for locally convex topology generated by all the seminorms you get, P a seminorm on G, if R is at least 1. Yeah? So well, okay, this is to impress you. Yeah, this is by no means an easy thing. The point is you have to estimate Baker-Campbell-Hausdorff terms. Yeah, and this is nothing I want to show you, and this is nothing you want to see. Yeah, believe me. But then at the end of the day, yeah, you get this kind of continuity property. Yeah, this is ugly combinatorics of Baker-Campbell-Hausdorff terms. And in the end, it boils down to say, well, we're doing some very rough overcounting. Yeah? We're doing all Baker-Campbell-Hausdorff words, yeah, in the Baker-Campbell-Hausdorff series, and we have a rough estimate how many there are. And we know that we can arrange things in a way that the coefficients in front, they stay bounded or something like that. Yeah? And then it's just estimating the number of terms. Yeah? The number of terms is then outbalanced by this factorial. That's in some sense the idea. Yeah? So it's a very brutal way to do things. I mean, it's analysis after all. Yeah? But it works. Yeah? And on the other hand, you can then show, well, you cannot do much better than that. Yeah, I mean, for R less than 1, it doesn't work. Yeah, so your brutal overcounting was not so bad in the end. Yeah, it was the combinatorics was kind of already wild enough that this holds. Okay, so this is half of the story. So we have found a topology here. We have found seminorms for that. And now the other thing is that what we need is then, of course, the product on the whole thing. We have to extend first of all, the product from the universal enveloping here to also functions on the Lie group. So let me just tell you what to do. So if we have smooth functions on the Lie group, well, then their star product is just a pointwise product. So there nothing happens if they don't depend on the momenta, functions being only depending on the position coordinates they commute in quantum mechanics. And so if we have then something like that, psi being in the symmetric algebra, that is also pointwise. That's the standard ordered thing. Yeah. So functions in the front are not differentiated. They're only differentiated in momentum directions as before. So if they don't depend on the momentum directions, then it's pointwise. And the only other thing is, what is this product? This is the one we have still to estimate. Yeah, the estimates here will be easy. Yeah, that's the pointwise nice product, only finitely many. Well, one term. Yeah, but here we will really get something. And so let's assume that this is something like, I should not write this psi. Okay, let's write this. This is psi1 symmetric tensor product psi k. Let's suppose these are a k-fold in the k-fold symmetric power here. If I specify this, then it will be enough. And I hope I get this formula correct now. So what do? We have an h bar over I to the power k, right? K, maybe not k, no, p, and p goes from 0 to k. Then there will be some combinatorial factors. And then if you have remembered Michael's talk, there will be now some summation over the permutation of these Lie algebra elements. So no, a couple of them survive. No, let's say I want them to act. The first p, they act on phi, and then the others, they survive. Sigma of k, and I have to symmetrize everything, and I think, well, there might be some factorials. I forgot. I think it's like that. Yeah, so there might be some factorials here. So what is the overall plan? Yeah, I mean it's the structure which is important here. Yeah, so we have this Lie algebra elements, viewing them as left invariant vector fields. They can act by Lie differentiation on the functions on the Lie group, and some of them differentiate. So we have p differentiations, yeah, and then some of them survive as polynomial functions on the cotangent bundle. Yeah? And we have to do it like in a standard ordered way, so phi gets differentiated, and that's the formula here. Yeah? And it's a finite summation. That's the good news. Yeah. So as long as we are dealing with all smooth functions and these guys here, we will have a trivially convergent star product. The point is, again, here we get the whole Taylor information by taking higher and higher psi's. We get the whole Taylor information of this smooth function. Meaning, again, by Borel's lemma, arbitrarily nasty Taylor information. Yeah? No chance for convergence. And the answer to the story is that, well, we have to extend. We want to extend our polynomials to the completion with respect to this topology here. Yeah, then we get interesting functions in the momenta. But that has a price that we are not allowed to take any smooth functions anymore, because now this having interesting non-polynomial functions in the momenta, this summation becomes infinite. Yeah? And now the idea is, well, we have to restrict the Taylor coefficient so that this summation still converges. Yeah? And this will be done at the group identity. Yeah? So we at least want to have this guy convergent at one point, right? I mean, this is not much to be asked. Yeah? So if this converges at the identity of the Lie group, then you see that that these were exactly the coefficients, the Taylor coefficient showing up in Michael's talk. Yeah? And again, there's a little subtlety. It would be enough if the absolute value of these coefficients have the nice property, but we put the absolute value inside. That's for technical reasons. This is needed, and it's not really clear whether these two things, but whether this really matters. Yeah? In any case, if we do that, and the upshot is, the theorem is that, and that is Oliver Roth Michael Heinz and myself, is that on these entire functions on the Lie group with this one here, so the entire functions, they have a locally convex topology coming from this Taylor formula. Yeah? This guy has the topology for R equal 1. Yeah? Star standard is continuous. Yeah? So that's then on the, of course, on the projective tensor product of the two. Yeah. So this is the continuity statement, and the idea is, well, we really have to estimate these kind of things, yeah, the convergence of this series, and that is exactly done by this entire functions. That's how they show up. And now you see, well, big question is, of course, how big is that space? Yeah. There, Michael gave you a nice answer that this is holomorphic functions on the universal complexification, at least in the case of a linear Lie group. Yeah? And then you can wonder, well, how do I describe global holomorphic functions on a complex Lie group? There are techniques, there are people doing that, right? I mean, that's one of the main issues in complex geometry, right? I mean, describing global holomorphic functions. Yeah? So there you can ask people who know things about. Yeah? And this is the space you get. Yeah? And then you can complete, you get kind of completion here and a completed tensor product of the whole thing that contains then some transcendental functions of the momenta, and we have a continuous star product converging nicely for all H bar in this situation. And you see, well, this is an example. It's already fairly involved, yeah? But still it's kind of explicit enough to really learn something about it. Yeah? So the topology is, it's not too bad. Yeah? You have a lot of features of this topology. Yeah? It's a nice Frechet topology. It has all funny, nice adjectives you find in textbooks on locally convex spaces. They apply, so it's Montel, it's nuclear, it's blah, 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 blah. All kind of nice features tell you that in the end you have a reasonably nice locally convex or Frechet topology and a Frechet algebra. I should stop here. Sorry, 5 minutes over time.
Stefan? Yeah, thanks for this great talk. Are there some questions?
Does it help if your group is somewhat special, compact?
Yeah, well, then of course you know more about that. Yeah. The point is, what you know in general is that matrix elements of finite dimensional representations, they are always in here. Yeah. So the moment you have a compact group, you know, for example, that the space of all matrix elements, yeah, that's point separating and dense in many aspects. It's not really clear to me. I think this we have not yet, we're not able to show that they are also dense in this topology in E. Yeah? Because this is a very fine topology now, and it's so it's not really clear if the matrix elements exhaust by completing them. Yeah? With this topology, the funny topology I gave you, yeah, of this one, I think that there's a good chance that this is true. Yeah? We are
This
still
should be true by Peter Weil. You can do that now because they're holomorphic things.
Okay.
Like my theorem gives that.
Yeah, right. Yeah, and on the holomorphic side, this is easier. Yeah. So okay, yes. So in some sense, matrix elements are enough to determine this space, yeah? At least for linear Lie groups. Yeah. And otherwise, well, this space becomes kind of more tricky, and then you have to wonder. You ask yourself why you're not working with linear Lie groups. Yeah. Why you're really interested in general Lie groups. Yeah. So okay, that's provocative. Yeah. But and well, we can of course also try to determine certain elements in the completion. How big is the completion? Yeah. In particular, how many functions of the momenta do we get? Yeah? And you see that, unfortunately, R equal 1. I mean, that gives the biggest completion. R equal 1. That excludes the exponential functions. just a little bit. Yeah? So, but that's just the boundary case of exponential functions. So they are unfortunately excluded here. Yeah? Just. Yeah? But okay, something with a little bit less growing Taylor coefficients is in there. Yeah? You still can try to use that whole machinery, and this is where we are only about to start, to do now really Lie theory, doing representations. And the point is, one application of this, and this has been shown in examples to work, not in for general G, is that we get kind of automatic self-adjointness proofs for certain Lie group representations. Yeah? If you have some infinite dimensional representation of your Lie group, you wonder whether certain infinitesimal generators are actually self-adjoint or not. Yeah, and that's a problem. Yeah, I mean this can be helpful. This is kind of if this representation comes from a representation of this Frechet algebra, and there are good reasons and good situation where this is easy to achieve, yeah, by some GNS construction for this algebra, then these guys here sort of are the source of a lot of analytic vectors for the representation, and then you can use this Nelson technology to get self-adjointness and things like that. Yeah? So this will be a machinery, an explanation, if you want, why under certain assumptions Nelson theorems apply, yeah, and give you self-adjointness in representations.
Is there the seminorm that you have in the Lie algebra? Is there any interaction with the Lie bracket?
Well, okay, I cheated a little bit. I mean, the point is, as long as we are looking here in finite dimensional things, yeah, then simply the Lie bracket is always continuous. Any bilinear map in finite dimension is continuous, and so I have to take all of them. Yeah, I could take one norm, but I need all multiples of the norm as well. Yeah, this is why these guys are really many. Even if I start with a norm space here, I need to take all multiples, and you see that the multiples, they get tensor powers of multiples, get the multiple to the power r. Yeah, so they become inequivalent norms on the whole thing. Yeah, even if you start with two norms which you can mutually estimate by multiples. Yeah, this estimate gets lost here. Yeah, so in finite dimensional, this is all you need. Yeah, I mean you can also say, well, I take here a norm, and then I take all constants to the r in front and call this something like that, and have to do it for all constants c. Yeah, that would be the same topology. And then in the continuity estimate here, you need that the Lie bracket is continuous. In fact, what you can do, and what we did in this paper, is you go for a generic Lie algebra, which has already a topology, some locally convex topology, such that the Lie bracket is continuous, but that's not enough. You need kind of locally submultiplicative seminorms for the Lie bracket. You would need a defining system of seminorms such that this holds with the same seminorm here on the right-hand side. Yeah? So if you have a Lie algebra, maybe infinite dimensional, where you have a topology generated by seminorm satisfying this property, then this still holds. Yeah? So in finite dimension, this is easy to achieve. Yeah? So you take any norm large enough, and then this holds. Yeah? But in infinite dimension, this really becomes a condition. Yeah? And then, but you have examples in infinite dimension as well.
Is there anything you can say with the relationship of the classical topology, the Frechet topology on C infinity, restricted to the polynomial? Do these things have any relationship?
These guys are way finer. They are way finer. I mean, all the seminorms of the C infinity functions, they are continuous for this one as well, but they are more. I mean, the C infinity topology is coarser. Yeah. In particular, all points are continuous. All evaluation functionals are continuous, still continuous also here. Yeah, which this is nice to have. I mean, the completion of this guy is not just an abstract completion, but they still have the interpretations of being functions. Yeah, because point evaluations are continuous. Otherwise, this would be kind of a more weird completion. Yeah, I mean, this is of course, this also happens in math, right? That point evaluations are not continuous, but then you have weirder interpretations of the elements in the completion. Yeah.
Question: what if you instead look at, instead of the tangent space, the cotangent space? Does anything interesting happen?
Well, this is the cotangent space here.
Sorry, the tangent space.
Then the point is you don't have a canonical Poisson structure on the tangent bundle. Yeah, this is why I take the cotangent bundle. In case of a Lie group, this means identifying the Lie algebra with its U. So the moment you choose a scalar product, you have this identification. But then this identification in general is not compatible with all the symmetries you have. You would need an invariant inner product to identify. This you might or might not have. In the compact case, you always have that, yeah. But then there's not much of a difference. Yeah. This is more intrinsic. The point is that in the compact case, yeah, this space also, this was also, I think, mentioned in Michael's talk. This is the complexification of G. Yeah, this in a, I mean, at least topologically, yeah. The Lie group structure is very complicated, yeah. But as a manifold, this is the complexification of G in the compact case. Yeah, I mean this is but the Lie group structure of the complexification pulled back to this one here is very complicated. Yeah, this is not easy. Yeah, it's not the semi-direct product of the vector space G star and the Lie group G. This is way more complicated, more non-commutative in general. Yeah.
May I come back to this question about the class of entire functions?
Yes.
Whether you really need it to be extensible to entire functions on the complexification.
Yeah. Mm-hmm.
So does anything break down in your continuity proof if you take just entire functions in the real sense?
What do you mean by entire functions in the real sense?
Well, about every point they have a convergent series.
That I would call a real analytic function. If I don't have any control over the radius, that would be a real analytic function.
Well, yes.
Yeah?
Okay.
Entire really means that the Taylor series converges everywhere.
Okay, so I mean real analytic.
Yeah. So then these coefficients here, in general, can blow up too fast. This really can go wrong. I mean,
this happens already for R2. Like
yeah,
the toy example.
Yeah, this you can do in the R2 case if you have just a real analytic function of Q's, and the piece done like that. Yeah, I think what you do is you take something like that. Yeah, so this is a perfect real analytic function, having singularities at I and minus I. So radius of convergence around 0 is 1. Yeah, and I think if you compute star products of these guys, they will blow up.
So you can't even bound the kind of location of the complex singularities away from the.
That doesn't help. This doesn't help. I think if you I don't know if I remember the example correctly, but I think if you do something like that, this will have radius of convergence 0 in H bar.
Okay.
Everywhere, at least at 0 or something like that. Yeah. So you, and this is not easy to. This is not difficult to check. You have to write down the Taylor expansion of the two things at 0, which you know, and plug it into the star product formula, and then you see that for no H bar, this has a chance to converge. The Taylor coefficients blow up too fast.
Okay, thank you.
Yeah. You can even scale that. You can move the singularities away or further. This doesn't help. Yeah, this doesn't help.
So you said the ultimate goal is to get some C-star algebraic completion of the observable algebra?
Yes, not achieved. Yeah.
Oh no, but I'm just wondering, so that would mean that, so you could represent that C-star algebra in a Hilbert space, and then your observables would be bounded operators.
Yeah.
Which to me sounds a bit strange, because usually a lot of the observables are unbounded operators,
yes,
because they have unbounded spectrum.
No.
So how does that fit together?
No, of course. You see, I mean, here I'm making things even worse, right? I have polynomials in the momenta, and now I have almost exponential functions in the momenta. Yeah, and no matter whether there's an I in front or not, yeah. So there are very, very unbounded guys in here. Yeah. So the idea is more the following. So let's call this completion here A. Yeah, and we have a nice Frechet topology. So this is Frechet. Yeah? Now suppose, well, it also is a Frechet star algebra. Have not talked about that, but you can cook up a star involution, which is just pointwise complex conjugation in the end. Yeah. So this doesn't work for the standard ordered star product, but there's a similar version where this works. Yeah. So you have a star involution. So it makes sense to look for positive functionals in the sense of A bar star A being positive. Yeah. Such a functional. And now suppose that this is also continuous. Yeah? This is also continuous for the very fine topology here. So it's not very difficult for a functional to be continuous. Yeah? This is not very demanding. The topology here is super fine. Yeah? In particular, point evaluations or something like that will be continuous. They will be not positive, maybe. Yeah? This is the failure. But continuity, that's kind of cheating easy. Yeah? Like in distribution theory, right? You have test functions have a super fine topology, so essentially all functionals on them are continuous. Yeah? So suppose you're in that situation, then what you can do is you can write down the usual GNS pre-Hilbert space. Yeah? So this J omega is just those algebra elements where this thing is zero. Yeah? It's Gelfand left ideal. Yeah? And so that is a module for H. Because the omega was continuous, this is a closed subspace. You divide the Frechet algebra by a closed subspace, so this is a nice Frechet space again. So this is Frechet again. And you have, now it's getting messy, but you can sort of define of the equivalence classes in this quotient, you can define an omega inner product by taking this guy as you know it from C-star algebra theory, right? You have so this becomes a pre-Hilbert space. And now the additional feature is that everything you do is continuous with respect to the Frechet topologies. Maybe not with respect to the Hilbert space or pre-Hilbert space topology coming from that inner product. Yeah? But for the Frechet topology, this thing is continuous, the module structure is continuous, everything is nice. Yeah? And so you get, from convergence series here, you get convergence series of operators in the Frechet topology of this guy. Yeah? And now this happens to be a pre-Hilbert space, and it happens to have a Hilbert space completion. Then all these guys become unbounded operators in the Hilbert space sets, but still you have a way finer topology where everything converges nicely. And that is in some sense the mechanism how to prove that many of these elements in here, they will be unbounded operators, that's true, yeah? But they will be self-adjoint. Yeah? You get from convergence properties in the algebra for this very fine topology and this very fine topology of this Frechet space. Yeah? You have maybe a lot of analytic vectors, and you can apply Nelson's theorem. Yeah? So this is a mechanism how to apply Nelson's theorem in a pretty generic automatic way. Yeah? This is autopilot proof. Yeah? And then, of course, once you have self-adjointness, you can say, well, these operators, well, they are not a C-star algebra, sure, yeah? But they determine spectral resolutions. They have spectral projections. And therefore, I take the von Neumann algebra generated by these projections, and then these operators will be affiliated. Yeah? And that's, in some sense, the final goal you have. Then you have found the good von Neumann algebra if you want. Yeah? Of course, you have to choose such a guy. Yeah? This means choosing a representation. Yeah? But this is kind of not so difficult then. Yeah, this is achievable. Yeah, we have many examples of these omegas leading to interesting representations.
Or can you take some sort of universal representation where you take the direct sum over every linear?
In principle, you could do that, but that will be, I guess, very big. And then you have a very big direct sum of Frechet spaces, which needs not to have a good topology anymore. Then this kind of, well, I don't know, but this kind of breaks down then. I mean, for Hilbert spaces, you know that you can handle arbitrary direct sums. They always will complete to a Hilbert space again. Yeah, but this is not clear here how to put on arbitrary direct sums of Frechet spaces again a Frechet space structure, or even a locally convex completed topology. I mean, there's of course the direct sum topology, but that's typically not very useful and too fine, and so there are some issues then probably. Yeah.
Okay, thank you.
Okay.
You're running a bit out of time, so if there are some questions from the online audience, this is the right time to ask them.
There is one.
There's some comments.
There's some in the chat.
No, these are just chat, like
just chat.
Okay. Okay.
Karen being upset when you mentioned something about these chapters and not getting.
So yeah, sure. Apologies.
Okay, then let's thank Stefan for the nice talk.
Thank you.
So next week there will be no seminar, but in 2 weeks there's Sebastian Halbig. He's going to speak about something I don't know yet. So see you in 2 weeks. Bye.